Hey guys, this is Mr. Lowry. This is going to be a video to help you get started with your homework and to help you with 10.5, which is about independent events, the probability of independent events. This section, the homework for this section is actually really easy. It's not going to be difficult for you at all. The hard part of this lesson, I think, is fitting in the concepts that we already know with new concepts in a way that will set us up for the next section. Okay, so in order to do that, I'm going to go back and talk about some things that we've already talked about so that I can connect it to this new idea, and that will allow us to connect it to the next idea tomorrow. So this may be stuff you already know, but bear with me because I think it's going to be important to kind of map out where all this information goes and connect the dots. Okay, the first thing we have to kind of talk about or review is the idea of inclusive versus mutually exclusive. Okay, if we want to find the probability of an event A or an event B from happening, there's something that we have to consider. And it's the idea of inclusive or mutually exclusive. Can these events happen at the same time, or is there overlap in the sample space between event A and event B? So in these Venn diagrams, the box that they're in represents all the possible outcomes in the sample space. Okay, here's the number of ways event A can happen, and here's the number of ways that event B can happen. The overlap here, this little section where they overlap, is where A and B happen at the same time. Okay, this is going to be an important idea because we're going to be talking about A and B happening in this lesson. So this little guy here, this is the overlap. A and B is the overlap. Okay, now A or B represents anything that's shaded. So all of the stuff where A happens but not B would be like this moon shape. All the stuff where B happens but not A would be this kind of moon shape, and then the middle piece here. So if we want to find all the possibilities where A or B happens, it's all of this shaded area. So to represent that, A or B is all the area from A plus all the area from B. But notice if we do that, we just counted this middle piece twice because this piece is a part of A and this piece is also a part of B. And so what we have to do is we have to subtract out the overlap. We have to subtract out the number of outcomes where they both happen. So when you have inclusive events where they overlap, the probability of that space is the probability of A plus the probability of B minus the overlap because you counted it twice. You don't want to count it twice. Okay? Over here, events are mutually exclusive, which means there's no overlap. So if you want the probability of A or B, that's just all the area of A plus all the area of B. And again, this area really represents the outcomes, the number of outcomes, and then probability would be number of outcomes divided by sample space. So all the ways event A can happen, all the ways event B can happen, there's no overlap between them. So if I want the probability of A or B, I don't have to subtract out the probability of them both happening at the same time because there's no outcomes where they both happen at the same time. There's no overlap. So that's the difference between inclusive and mutually exclusive, right? When we're talking about A or B, ors here, we're just going to add the separate probabilities of the separate events, and in this case we have to subtract the middle. So the main idea here that's important is if you're doing an OR probability, you're adding. Okay? Sometimes you have to subtract some extra, but the whole idea is we're adding. Okay? Let's look at a couple specific examples here, and this will help us kind of lead into what we're going to be talking about today. Okay, so here I have represented a Venn diagram for specific events that are inclusive, meaning you have events that overlap, outcomes that overlap, and you have mutually exclusive. Okay, so let's say I wanted to find the probability of black or jack. So I'm pulling one card from this deck, and I want to find the probability that it's black or a jack. Now we already talked about this example, but here's the idea. There's 26 black cards in a deck of 52 cards. Half of them are black. So this circle, notice there's 26 black in this circle, 24 plus 2, 26 total. Okay, the ones that are in just this section are the cards that are black but not jacks. Then here are the cards that are black and jacks, and here are the cards that are just jacks but that aren't black. Okay, in that kind of semicircle. So there's 4 jacks total, right? 4, 2 plus 2 in the jack circle. There's 26 blacks total, 24 plus 2 in the black circle. And then again, this is black and jack. And this is kind of what we're going to be talking about more today, is the and scenario. So and is that overlap, okay? There's 24 cards that are neither black nor jack. That's what that 24 represents. And there's 52 cards total. Okay, so if I wanted to find the probability of getting a black or a jack, that's 24 plus 2 all over 52, right? So if I do the probability of black, that's 26 over 52, right? 26 out of 52. And then I add to that the probability of a jack, that's 4 out of 52, right? Because there's 4 here. Notice I added that 2 twice, because that 2 is in this 4, and that 2 is also in that 26. So this is 24 plus 2 plus 2 plus 2, and I used that 2 twice. So that's too many things. So I have to subtract out the middle part, the and, the probability that they is black and a jack, the probability that they both happen, which is 2 out of 52, because there's 2 black jacks. Okay, so that's going to be 30. 26 plus 4 is 30, and then minus 2 is 28 out of 52. And then we reduce that, and that's 7 over 13. Okay, so that's just another example. When we're talking about or, we're going to add. Okay, in this case over here, these are mutually exclusive. So if I want the probability of drawing a number card or a face card, there's no overlap. I just want this, the number of outcomes here divided by sample space, plus the number of outcomes here divided by sample space. And if I just add this number to this number, I get all the possible outcomes where either happens without doubling up on that overlap. Okay, so what we're going to talk about more specifically is this now, right? We talked about or. That's all the or stuff. Now we want to talk about the and stuff. What's the formula for and, or how do we figure out and, right? We have ors here, but what about this guy? Okay, where does that come from? And what are some facts around the and? Let's talk about that for a minute. Okay, so let's talk about the probability of black and jack. Okay, now we know it's 2 out of 52, right? We know that this is 2 out of 52, which equals 1 out of 26, because there's 2 black jacks out of 52 cards, right? But this is kind of like a compound probability. So let's break it up and let's figure out how we could kind of derive this using the fundamental counting principle. Okay. The fundamental counting principle says if there's m ways for one event to happen and there's n ways for another event to happen, then there's m times n ways for both of them to happen. Okay. So we're going to use that fundamental counting principle. So let's think about that for a second. How many ways are there to pull a black card? Well, there's 26 of those, right? Okay. How many ways are there to pull a jack? There's 4 ways. Okay. So how many ways are there to pull a black jack? Or sorry, how many ways are there to pull a black and a jack? So this is kind of like if we're talking about 2 different events, right? You pull a card out and it's black. You pull another card out and it's a jack. So right now we're kind of considering these as 2 separate events. We're not pulling a card once. We're pulling 2 separate occasions. So the probability of pulling a black card from a deck, or sorry, the number of ways to pull a black card out of a deck, there's 26. The number of ways there are to pull a jack from a deck, there's 4. So how many ways are there to pull a black card and then a jack later? This is going to be 26 times 4, which is 104. Okay, so there's 104 ways in 2 pulls to pull a black card, put it back in the deck, and then pull a jack out. 104 ways for that to happen. Okay. So we're going to call this the event A that we're looking for. Okay. If we want a probability, we have to actually divide that by the how many ways there are to pull 2 cards from a deck. So we're talking about 2 different events here. How many ways there to pull card 1? There's 52. How many ways there to pull card 2? There's 52. Right? So 52 times 52, figure out what that is. It's going to be a big one. Okay, it's 2,704. So this is the idea, is if I'm pulling 2 cards and each one is an event, I can think of it, let's just think about how many ways there are to do that. So event 1, pulling a black card. How many ways are there to do that? 26. Event 2, pulling a jack. How many ways are there to do that? There's 4. So how many ways are there to pull a jack from a deck once, and then the second event is pulling another card and it's a jack? There's 104 ways for that to happen. Okay? Then we kind of look at the problem separately, and we look at, well, how many ways are there to just pull any card, right? How many ways are there to pull a card once? There's 52 ways to do that. How many ways are there for you to pull a card the second time? There's 52 ways to do that. So in total, there's 104 over 2,704 ways to pull a black for your first card and then a jack for your second card if you're doing 2 pulls. Sorry, I had to grab my calculator. Okay, so let's just simplify this fraction here, okay, and let's just see what's going on. So we have 104 divided by 2,704. Actually, let's do it in fraction form. 104 over 2,704. Okay, it turns out to be 1 over 26, right? Okay, what does this tell us? Or, what do we got going on here? Okay, the idea behind this is the probability of A and B is the same thing as the probability of A times the probability of B. Because if you think about it, this right here is the probability of pulling a black card. And this right here is the probability of pulling a jack. All right, so when you use the fundamental counting principle separately, you use the fundamental counting principle kind of on the top of this equation to figure out how many ways are there to pull a black card on your first draw and a jack on your second draw. And then on the bottom, use the fundamental counting principle to think, well, how many different ways are there to pull a card and then pull another card? You get the same probability. So the idea is when you have an and, the probability of 2 events happening at the same time is the probability of the first event times the probability of the second event. Okay, so again, let's go back. Or, if we have an or situation, that means we're adding probabilities together. If we have an and situation, that means we're multiplying probabilities together. And this goes back again to the fundamental counting principle, just figuring out how many different ways there are for something to happen. Okay, now this right here is an important key concept for today, and the one that you're going to be using for a lot of your assignment. So this is a really, really easy and simple idea to come up with. The problem is, how does that fit into the rest of the picture, right? Like, we're talking about ands, right? We also talked about ors, though, but even within the or situation, you have some ands sometimes. So this little kind of sliver here, this overlap piece, kind of fits into like a bigger picture as well, and so that can be a little bit confusing. Okay, the other thing that's tricky about this is only true in a certain case, and we need to talk about that, and we need to talk about independent events. Okay, so this is a really important concept. Now, you could do most of your assignment today just using this without knowing what independent events means. But in the next lesson, we're going to talk about dependent events. And so to set up for our next lesson, we need to talk a little bit about independent events versus dependent events. Okay? So this is the deal. Notice that I have 52 cards here and 52 cards here. What happened is when I thought about pulling this card, I replaced the card to pull it again. Or you could think of it as pulling from two separate decks, right? So in order for these to both be 52, they have to be independent events, which means that whatever I drew from the first time can't affect the second draw. In other words, if I pick a black card, I got to put it back and redraw over again, reset. Otherwise, the probability is going to change. We don't want the first event to impact the second event. Okay, so this is only true when the events are independent. In other words, one event doesn't affect the other one, or the outcome of one event doesn't affect the other one. Okay, so let's go jump into the book really quick. Okay, this is on page 660 at the very top, and this is really important here. Okay, two events are independent if the occurrence or non-occurrence of one event has no effect on the likelihood of the occurrence of the other event. Meaning one event doesn't affect the other one. If two coins tossing is independent, right? The outcome of the first one won't affect the outcome of the second one. If one does affect the occurrence of the other, if one event does affect the occurrence of the other event, then the events are dependent, okay? So I took a lot of time to talk about the difference between independent and dependent. You're not going to have to use dependent today. You're not going to have to worry about that, but you will in the next section. So we wanted to talk about that, okay? And this is what this says. So events are independent if and only if the probability of A and B is the probability of A times the probability of B. So going back to this idea that we talked about here with our deck of cards, right? Either way, whether we multiplied the probabilities separately or whether we just took it out of the same deck, we get 1/26 either way. So this is true only if one event doesn't affect the other event, okay? So real quick, before we jump into some example problems, let's look at one from 10.6 just to distinguish the difference between independent and dependent. Okay, so let's take a look here. In this example problem, we've got 9 red marbles and 3 green marbles. Okay. Don't tell anybody I wrote in my book. All right, so let's look at independent events versus dependent events. Okay, so what I'm going to do is we're going to pick 2 marbles from these 12 marbles, right? We're going to pick twice. The first time, event A is pulling a red, and event B is pulling a green. But the idea is the marble is replaced. Okay, so the first probability, there's 9 reds out of 12. So the probability simplifies to 3/4. This is the probability of pulling a red. Now, if I pull the red and then I replace the marble, that kind of resets all the probabilities. So I still have 12 marbles for the second roll, or the second choosing, excuse me. Okay, the second one, I need to pick a green marble, and there's 3 green marbles out of 12, which simplifies to 1/4. Make sure you can see that. My writing kind of light in my book. So there's 3/4. 3/4 is the probability of picking a red. 1/4 is the probability of picking a green. And so if you multiply that together, you get 3 out of 16. Okay, that's if the events are independent, meaning the first pick doesn't affect the second pick because I replaced it. Okay, dependent events is a little bit different. So in this case, we're not going to replace the marble. So whatever happens, whenever I pick that first one, then I have to figure out what's the probability of assuming that happens. Can I pick a green one? So again, the probability of picking a red is still 9 out of 12, which is still 3/4. Okay, but as soon as I pick that marble, I can't pick that one again because I'm not replacing it. I'm not resetting the probability. The second pick, the second marble pick, depends on what the first pick was. So this notation here, we're going to talk about this more in detail tomorrow, but this is saying what's the probability that B happened, assuming that A happened first. Okay, so if I pick that red one out, then there's still 3 green marbles left, but there's only 11 marbles to choose from because I already picked out one of them. And so this probability, notice, is different than this probability. So the probability of picking a red and then picking a green is different if I replace the marble than if I don't replace it. And that's the difference between independent events and dependent events. Does the first event affect the second event, or the probability of the second event? Okay, so again, taking a lot of time to talk about the difference between these, not so much because you need it in this lesson, but because I want to put it in context so that the next lesson makes a little bit more sense. And also we connect it to things that we've already talked about before. Okay, so let's jump back here and let's look at a few example problems. And then we'll get started with the homework. Okay, so example 1. A bag contains 9 red marbles and 3 green marbles. That's bag A. Bag B contains 9 black marbles and 6 orange marbles. So a couple things to notice, first of all, is that these are totally separate bags of marbles that we're pulling from. So whatever I pick from bag A is not going to affect what I pick from bag B. And so what that means is the events are independent. Okay, that's a super important idea. So we want to find the probability of selecting 1 green marble from bag A and 1 black marble from bag B. Well, that's pretty easy to do. Okay, so again, bag A, let's write some of this stuff down. In total, bag A has 12 marbles, which is 9 red and 3 green. Okay, and then bag B, we got 9 and 6, which is a total of 15. Okay, so 9 black and 6 orange. Okay, and we want to find the probability of selecting 1 green marble from bag A, there's our keyword, and 1 black marble from bag B. So remember, if we want the probability of A and B, two things happening, how do we do that? It's the probability of A times the probability of B, right? If the events are independent, which we know that they are. So that's all we have to do. We just have to multiply these. So the probability of selecting 1 green marble and 1 black marble, 1 green from bag A and 1 black from bag B. So the probability of the first guy is the number of green marbles, 3 out of the total. So probability of A is 3 out of 12. 3 green marbles out of 12 marbles in the bag. Okay, and then we want to draw 1 black marble from bag B. So 1 black marble from the bag, there's 9 black in the bag, and there's 15 total. Okay, so that's what we're doing. We're just multiplying. We find the probability separately, we multiply them together, and that's the probability of A and B happening together. It's basically using the fundamental counting principle again. How many ways are there to draw a green marble? There's 3. Oh, sorry. Well, there's 3, excuse me. How many ways are there to draw a black marble? There's 9. So how many ways are there to draw a black marble and a black green marble? There's 27 ways for that to happen. That's the fundamental counting principle. Okay, well, how many ways are there to just draw a marble from bag A? Any marble. There's 12. How many ways are there to draw a marble from bag B? Well, there's 15. So how many ways are there to draw a marble from bag A and then a marble from bag B? What are all the different outcomes? Well, that would just be 12 times 15, or 180. Okay, so what we have is 27 over 180. We'll write that as a fraction so we can simplify it. And that's going to be 3 over 20. Okay, so that's the probability of A and B happening because these are independent events. Now again, you're not going to have to worry too much about if events are independent or dependent on this assignment. You're just going to kind of assume they're all pretty much independent. And then later we'll talk about dependent events and kind of how to do that. So that's kind of the idea, and we want to connect this formula, this multiplying idea, to the fundamental counting principle. Basically, we're using the fundamental counting principle on top of this fraction to figure out how many ways can we get the outcome that we want. And then we're using the fundamental counting principle on the bottom of this fraction to figure out the sample space, or how many different possible outcomes are there for two different bags of marbles. Okay, so 3 over 20 is 0.15 or 15%. Okay? All right, let's jump into the homework. So I gave you guys 4 and 5, so that's these two. So bag A contains 5 black marbles and 5 white marbles. Bag B contains 1 green marble and 2 red marbles. Find the probability of selecting a black marble from bag A and a green marble from bag B in 2 draws. Okay, so we want basically the probability of A and B, which we know is the probability of A times the probability of B, because these two events are independent. They're two completely separate bags. The marble that I draw from the first bag is not going to affect the marble from the second bag. Okay, so I'm going to let you guys go through that one. It's going to be set up very similar to the one we just did. You'll figure out, how many marbles are in bag A total, how many marbles are in bag B total. I'll give you a hint. There's 10 over here, and there's 3 over here, and you can fill in the rest, right? But remember, this is going to be a multiply, because we're talking about and here. Okay, let's look at the next one. Number 5. 2 students, 1 from each science class, are asked randomly to select and attend a national science conference. So 1 from each science class, so there's 2 different science classes. We're picking from 2 completely different sets of people. So the student that I choose from the first class is not going to affect the student that I choose from the second class, which means these events are independent, which is important. Okay, so Melinda is in this class of 22, Seth is in this class of 19. We want the probability that both Melinda and Seth will be selected. Well, that's going to be multiply scenario, right? We just want to find the probability of each event individually and then multiply those probabilities. So I'll let you guys work on that. Okay, you have some problems from this set. I think I gave you 9 through 12. So let's just do one of them. Okay, so number 7. Start with number 7. Okay, A, B, C, D are independent. Probability of A is 0.5, the probability of B is 0.25, the probability of C is 0.275, and the probability of D is 0.1. Find each probability. So this is going to be super simple. Probability of A and B equals the probability of A times the probability of B, because they are independent. Probability of A is 0.5, probability of B is 0.25, so we just got to do 0.25 times 0.5, which is 0.125. And that's it. That's all we got to do. We know they're independent, so the probability of A and B is the probability of A times the probability of B. Whoops. Since they give you those probabilities, you're just multiplying here. No big deal. Okay, let's look at number 17. I'm just going to look at kind of one from each little section here. Sorry. Okay. All right. Refer to the spinner shown, which each number section is exactly 1/8 of the circle from the probability of each event in 3 spins. Okay, so we want to find the probability of all 3 numbers are 3 or greater than 5. Okay, so this is going to be kind of tricky because there's this 3 or, right? So there's this or situation. But we also have 3 different spins, okay? So that there's actually going to be 3 different events, which means 3 different probabilities, okay? So we got 3 different events, and we want to find the probability of each separate event and then multiply them all together. The probability of all 3 of these events happening at the same time is the product of the three different probabilities. Okay, so what's the probability of getting a 3 or greater than 5? And there's 8 different options. Well, out of those 8 options, we got, so 1, 2, 3, 4, 5, 6, 7, and 8. Which ones are 3 or greater than 5? This one, this one, this one, this one, and this one. Okay? So these are, the or part right here, this guy right here, this means we're going to add them together, add the probabilities. Right? What's the probability of getting a 3? 3 out of 8. What's the probability of getting, oh sorry, it's not 5 or greater, it's greater than 5. Sorry. We're just going to add, probability of getting a 3 is 1 out of 8. The probability of getting greater than 5 is 3 out of 8. So together, the probability of getting a 3 or greater than 5 is 4 out of 8, which is 1/2. Okay, but that's just for one spin. So there is an or situation in here, for sure. They happen to be mutually exclusive, so we just add the probability of 3 to the probability of greater than 5, and we get this guy. That's the or part, that's the adding part. Okay, we add 1 out of 8 to 3 out of 8. But then we have to take the idea that we're spinning 3 times. Right, 3 like separate events, and we want to have that same outcome every single time that happens. So probability of happening on the first spin is 1 out of 2. The probability of that happening on the second spin is 1 out of 2. And the probability of that happening on the third spin is also 1 out of 2. So altogether, that's 1 out of 8. 2 times 2 times 2. So there's a 1 out of 8 chance that every single time you spin, you get either a 3 or greater than a 5. So this is why I went through all the trouble of, talking about the ors and the ors and the ands. Or you're going to add, ands you're going to multiply, but there's kind of a implied multiplication. That doesn't say the word and, but it's the probability of 3 or greater than 5 and 3 or greater than 5 and 3 or greater than 5. Because it's all 3 numbers are going to be that way. Okay. Okay, let's take a look at 24 through 26 really quick. Okay, so it says, suppose a security system consists of 4 components: a motion detector, a glass break detector, magnetic door and window contacts, and a video camera. The probabilities of escaping detection by each of the 4 devices are 0.2, 0.3, 0.4, and 0.6 respectively. So these are each probabilities so this is the probability of escaping the motion detector, the probability of escaping the glass break detector, the probability of escaping the magnetic door and window contacts, and then the probability of escaping the video camera. Assume that all components act independently, so one's not going to affect the other. So let's look at 25, because that's the one you have an answer for already, and then you guys can do 26 and 24 and 26. So what is the probability that a thief can get past the glass break detector and the motion detector? So again, the probability is 25. Probability of A and B is equal to the probability of A times the probability of B. Now, you can label these however you want, but let's just say that the probability the thief can get past the glass door detector, that's A. So glass door was, glass break detector, that's this one. That's this one. Okay. And then the probability you can get past the motion detector. Motion detector was the first one. So all we have to do is multiply the independent probabilities. The probability of him getting past, the thief getting past both of those, is just each one separately multiplied. And this is going to give you, I think it's 0.06. Let me double check. Yeah. Or 6% chance of that happening. Okay. So again, the idea is if the events are independent, multiply each probability separately, and you'll get your probability of both happening. It's essentially the fundamental counting principle, only with probabilities instead of with just outcomes. So, but it works kind of the same way. All right, that should get you started on your homework. That should help you get through this. Again, this is going to be a super, super easy assignment for you. The main thing is making sure we have like the right definitions and terms down, and to make sure that you understand that later on there's going to be what we call dependent events. So how they all work together is going to be important for you.